push that rock here with Simpson Math. Let's demonstrate how to transform a vector using a matrix as a function. Okay. So what I have right here is a matrix. It's 2 by 3, meaning it has 2 rows and 3 columns. We call these the rows. That's what a matrix is. It's just an organization of objects in rows and columns, an array. So we have rows and columns. And the types of matrices we're interested in are ones where the objects that are arranged are numbers. And when you have a matrix like this, it's a function. So this has 2 rows. It has 3 columns. So we say the size of the matrix is 2 by 3. It's a 2 by 3 matrix. Can we see all that? Yes, we can. Okay. Now, a 2 by 3 matrix is a function that, whatever the name of this matrix is, let's call it F, and it maps vectors from one space to another space. In this case, it's going to take 3 space vectors. That's how many columns there are. The columns determine what the domain is. It's going to take those types of vectors, 3 space vectors, and map it to 2 space, 2-dimensional vectors. The ones we're interested, that we're used to. 2-dimensional vectors are just points in a plane, X, Y. So that's all a vector is an ordered list of numbers. So if you have 2 numbers in the list, we call it an ordered pair, but that's just a 2-space vector. If you have 3 numbers in the list, sorry, my finger's broken, I need to be careful. If you have 3 numbers in the list, then it's a 3-space vector. It belongs into 3 space, the space we walk around in, where there's both an x-axis, a y-axis that we're used to, plus the z-axis, a third axis. Now, when it has 2 rows, then it's taking the vectors to 2 space. But when it has 3 columns, the type of vectors that it's taking to 2 space are 3 space vectors. So the input goes here. So we have an input vector here. And because this is a function that goes, whose domain elements are 3 space, I have to put a 3 space vector here. It doesn't make sense if I don't have a 3 space vector here, meaning I have 3 rows, okay? So now I'm going to demonstrate how this matrix transforms this into a 2-space vector. And the way you do it is with the matrix multiplication mantra. It's first entry in the input times the first column, plus, students forget the plus, second entry times second column, plus third entry times third column, and just keep going until you get to the last entry. In this case, we only have 3 entries, so we stop after 3. So let's repeat. It's the first entry in the input times the first column, plus the second entry times the second column, plus the third entry times the third column. Is that easy? I'll demonstrate now. Okay. We're going to take this first entry. Let me move this out of the way. Okay. Oh. Try again. Sorry. First entry in the input times this first column, plus second entry times second column, plus the third entry times the third column. Okay, now we just scalar multiply the vectors. This vector gets quintupled, so it's 5, 10. This vector gets quadrupled, so it's 12, 20. And this last vector gets tripled, so it's -3, 18. And then the way you add vectors is you add corresponding components. So I add 5 to 12 to get 17, minus 3 is 14. I add 10 to 20 to get 30, plus 18 more gives me 48. And that's the product, which the product, this is called the product, but it's the output vector. So we put in a 3-space vector, we got out a 2-space vector. Now before I go, let's do matrix multiplication, which is just repeated vector transformation. That's what matrix multiplication is. It's repeated vector transformation. And it's doing this, what we just did, over and over again. Okay. So here's an example. Again, we have our 2 by 3. So that means we're going from R3, going from R3, the number of columns, to R2. That's what this function is going to do. So the only way I can do the multiplication, is if I have 3 space vectors to transform. That means the matrix over here to the right, the matrix on the right side, must be storing 3 space vectors because I have 3 columns here. However many columns I have, that's what type of vectors I need. So if there's 3 columns, I need a vector with 3 entries, because remember, I'm going to take the first entry times the first column plus the second entry times the second column plus the third entry times the third column. So if I have 3 columns, I must have 3 entries. If I only have 2 entries, not enough. If I have 4 entries, too many. So for this to work, this must be a 3 by something. It must be a 3 by something. In this case, it's 3 by 3. I put 3 vectors in here. We're going to transform 3 vectors. But it must be a 3 by something. Okay? 3 by something. These 2 numbers must match up, or it doesn't make any sense. Because this matrix over here is just a storage bin of inputs. Well, the inputs have to belong to 3 space. So if it's not storing 3 space vectors, it's nonsense. Okay, so those must match up for that reason. And now we already did this. It turned out to be 1448. So our first output is 1448. This vector here turns into that vector there. So I have 2 more to do. I wonder what this vector is going to turn into. Well, to do that, multiplication mantra. First entry times first column plus second entry times second column plus third entry times third column. Well, 0 wipes that out. It becomes 0, 0. Doubling this, I get 6, 10. Multiplying by a negative changes the sign. So that -1 becomes a +1. And that 6 becomes a -6. And then we add straight across. So 6 plus 1 is 7. 10 and -6 is 4. And so this vector here, the middle vector, turns into 7, 4. So I get a 7, 4 over here. Can we see that in the screen? Oh my, I'm off the screen. Sorry. So to reiterate, this first vector turned into what we did a while ago, 48. And then this vector turned into 7, 4 because I did the transformation. It became 7, 4. So I put it over here in the second position because this was the second vector in the input. Okay, so we've got one last one to do. What does this become? Whatever it becomes, it's going to come over here and go right there. And to figure out what it becomes, you take the first entry times the first column over here, 1, 2, plus the second entry times the second column, plus the third entry times the third column. When you octuple 1 and 2, you get 8 and 16. 0 is going to make both of those 0. When you multiply by 0, you get 0. 5 times a -1 is a -5. 5 times 6 is 30. Adding across, I get 8, and a -5 is 3. 16 plus nothing is 16 plus 30 is 46. Math made simple. Simpson Math.